Hey YouTube, it's your boy Kenrick here again, aka the Optometry Prodigy, and I'm coming at you with another video. Before I say anything else, I must express appreciation and thanks for those who viewed, those who liked, comment section especially. I see you guys, those who shared the first video. I really thank you all for your support, and I look forward to it in the future as well. So as we jump into this other video, we're going to look at light, refraction, and thin lenses. This is geared more towards those who are doing foundational work in optometry, those who have now started, and even it will be applicable to those who are doing some form of physics discipline as well. So we're going straight into it. Light. So what do we know about light? From secondary school and so forth, we would know that light is the visible part of the electromagnetic spectrum, ranging from about 400 nanometers to about 760 nanometers. Light, though, we know that it acts such as a wave. It acts like a wave in certain aspects, and it also acts as a particle in other aspects. And we call this the wave-particle duality of light. But what do we mean when it acts as a wave? This brings into the equation things such as diffraction of light and even interference. And we can identify these areas through a simple experiment such as the Young's double slit experiment. When we talk about particles, though, we talk about how light has the ability to indicate the photoelectric effect. And when we talk about the photoelectric effect, we are talking about simply the emitting of photons, possibly from a surface as light hits a surface at a specific frequency. Another thing we want to talk about light is it can be discussed in three aspects of optics. It can be discussed in geometrical optics. It can also be discussed in electromagnetic optics. You're going to have to get accustomed to my handwriting. Electromagnetic optics and also quantum optics. But for the sake of this video, we're going to focus more on geometrical optics. Before we move on from light, though, you would want to remember equations such as the frequency of light is equal to the speed of light over the wavelength of light. Also, the energy of a photon from light is equal to Planck's constant multiplied by the frequency of the light. And using these two equations, and substituting the frequency, we can still find the energy of that photon by multiplying Planck's constant by the speed of light over lambda. So this is just to remind you of some of the equations that you will see when you're talking about light. However, let's look at the electromagnetic spectrum. So here we have the electromagnetic spectrum. As we can see, the energy increases as the wavelength decreases. As wavelength increases, energy will decrease. As we can see here, this is visible light. It expands here about 400, as I said, approximately 760 nanometers. You'd also hear a lot about ultraviolet light. We call it UVC, UVB, and UVA. All of them, they will fit into there. And also we have infrared light. An important thing to note here as well is that as the wavelength decreases and as energy increases, for us in terms of our health, we would know that this actually causes, or this side of the spectrum actually causes what we call forms of cancer, skin cancer, basal cell carcinoma, and other forms of skin cancers. As we know, UV light is not is not good for us as well, especially the E and B that we experience through simply exposure from the sun. However, UVC, we don't really get that exposure because it's blocked by the ozone layer. However, from simple welding and so forth, you can have the UVC affecting you as well. So these more affect, especially E and B, more affect what we call cataract formation. It can speed up the formation of cataracts. It can also cause some forms of damage to the retina. It also has a factor in the formation of macular degeneration as well, and other forms of pathologies in the eye. So that's just to mention there. So now we'd move on to the vergence of light. What do I mean by the vergence of light exactly? And vergence of light simply talks about the ability for light to converge and diverge, or rather I should put it is the amount that light converges or diverges. So vergence, the ability for light to converge or diverge. To speak about this, I'm just going to use an example. So we have a point source, and what we have happening is what we call divergence. So we have the rays going out in this direction. The rays are diverging. So in order to calculate what we call vergence, the formula is simply the vergence of the object or that point source is 1 over the distance from the point source or the object to whatever plane we are speaking about. So if we are speaking about a 2 centimeter distance, you can simply plug it into the formula. Also remember that this length is actually, once you plug it into this formula, you need to put it in as meters. So it will be 0.02 meters, and this will give us approximately minus 50 diopters. Why minus? It also should be here. Why minus is simply because once you're dealing with divergence, it's a minus sign convention we use there. So minus 50. But just simply to show you, as the wavelength of our light, as it goes out, it will decrease, and this or it will decrease. And simply to show that, if we go, let's say about 10 centimeters, once we plug that into the formula here, so we have 1 over minus 0.10. Again, remember to put this in meters. You'll get minus 10 diopters. So as you can see, it will continue to decrease in this direction. However, what about convergence? So again, we have a point source. We have light coming into that point source. And using the same formula again, divergence is equal to 1 over lambda. In this case, perhaps we're looking at an area over here from the point source. What will be the divergence at this point? Let's go 2 centimeters again. I remember this is convergent. This is a convergent system, so this will actually be plus. So when we enter it here, we don't need to put in that minus sign. We're looking at 0.0. Let me write that a little bigger. We're looking at 0.02 1, sorry, under 1, and that will give us plus 50 diopters. So here would be plus 50. And if you check it again, as we continue to move away from the point source, as that wavelength increases, power of this is going to continue to decrease. So how about 10 centimeters here as well? Plug it into the formula, 0.10, we're going to get plus 10 diopters. And one thing also we should look at in terms of vergence, there's something we also call the vergence relationship. And it's a simple formula as well. The formula is L, or object vergence, plus the power of a surface, or surface power, is equal to the vergence of the image. And using this formula up here, and since we are speaking about surface now, we need to take into account the refractive index of those surfaces. So it will be n over that distance, L, from the surface, power again, and the image here, we can calculate that as well. This will be n prime. N prime is simply the refractive index of that second, or that medium we are speaking about, over the distance of the image, from the distance from the image to the surface, or to the lens, or whatever surface we're going to speak about. And since I brought up the idea of refractive index, let's have a look now at refraction itself. So again, from secondary school, what is refraction? Refraction is simply the changing of light from its normal course because of a change in density as it travels from one medium to another medium. So refraction now. Let's look firstly at the refractive index. When we talk about the refractive index, it is simply, you can denote it as n, it's usually denoted as that, and it's simply the speed of light, c, in a vacuum, speed of light in a vacuum, over the speed of light in a medium, or whatever medium we're going to talk about. It could be crown glass, it could be polycarbonate plastic, it could be high index lenses, it could be from air to water. That is what we talk about when we say a medium. So let's go into a bit of an example to show some aspects, or to show refraction taking place. So here we have the interface of a surface. Above we would have air, and let's put the other surface, possibly something like crown glass, around 1.5 to refractive index. So perpendicular to the surface, the interface of the surface, that, as we said, from air to that crown glass, we're going to have what we call the normal. Normal is always perpendicular to the surface. And then let's draw now an incoming ray, what we call the incident ray. The ray is coming down, and that ray will make an angle to the normal, which we call the angle of incidence. However, as the light ray hits this surface, and it goes into a medium that is more dense, it is going to slow down. But it is not only going to slow down, it is going to refract, and as it refracts, it will refract towards the normal. And this will create an angle that we call the angle of refraction. So in this case, as we go from a less dense medium to a more dense medium, the angle of incidence is going to be more than the angle of refraction. Again, one thing to remember, it will actually go towards the normal. Therefore, theta prime will be less than the angle of incidence. So how about an example where it is reversed? Again, Let's go and draw the normal first this time. Then we're going to have our surface here, the interface. Let's go with A again. We're going to put the A below this time. Let's go with polycarbonate, about 1.58 of refractive index. So again, we have our ray of light coming in, as we call it, the incident ray. It's going to form an angle, theta to the normal, which is the angle of incidence. However, as we go from a medium that is more dense to a medium that is less dense, again it's going to refract. However, this time it is going to speed up and refract away from the normal, forming an angle again, theta prime. However, this time theta prime, which is the refracted angle, or the angle of refraction, is actually going to be more than theta, or the angle of incidence in this scenario, because now we are going from a more dense material or medium to a less dense one. Another major thing we need to note in cases of refraction is the total internal reflection. As the word itself says, what is total internal reflection? This simply occurs when the angle of incidence, we call theta, is more than the critical angle of a medium, to the critical angle of the medium. Okay, so let's look at an example for this. Let's just take the example of the 1.52, which is the crown glass. So to find the critical angle of crown glass, what we need to do is set the angle of refraction to 90 degrees. 90 degrees would be on this plane here. As it hits to 90 degrees, if we set that angle at 90 degrees, now we have to bring in what we call Snell's law. Snell's law is used to find refractive index, can use to find the angle of incidence, refractive index of the other medium, also the angle of refraction. So as I said, to find the critical angle of, let's say, crown glass, we're going to set the angle of refraction to 90 degrees. So 1.52 sine theta. 1 is going to be the medium, the refractive index of the other medium, and then we're going to have sine 90 degrees. And those of you who would know, sine of 90 degrees is 1, and we have multiplied by 1 here, so this whole side would be 1. And then we're going to transfer this to the other side, so we're going to have sine theta 1 over 1.52. In order to find theta, we do sine inverse of 1 over 1.52, and this will give us an angle of 411, or 41 rather, 0.1 degree. And this is a critical angle of crown glass. So therefore, what this simply means, if the angle here of incidence is more than 41.1, total internal reflection is going to occur. So let's just say we have an angle of 42 degrees here. This ray of incidence is going to reflect internally. It will not cross the barrier because the angle of incidence is higher than the critical angle. Now we're going to go into what we call secondary focal points primary focal points. So let's get into that. Before I go directly into the diagram, let's firstly speak about calculating the refraction, or rather refractive power of a surface. So the refractive, let's change the color here. So the refractive power of a surface so we have P, or rather the modulus of P, and to get that we need the refractive index of the medium, so n prime, and we also need the focal length, or the secondary focal length of, so basically secondary focal point to the surface, the refractive surface. Another way to calculate P is if we have the refractive index of this secondary medium and also the first medium that the light rays come from, modulus again, and all of that over the radius, or the radius of curvature of that refractive surface. So these are the two ways that we can calculate the power of that surface. And P, the refractive power, can either be plus or it can be minus. Plus is for the converging system, so converging surfaces, or surfaces that cause the rays to converge, or negative for the diverging surfaces, or surfaces that cause the light rays to diverge. So let us go into how we find, or how to understand, what is the focal points. So for the secondary focal point, we have some light rays coming in from left to right. We also have here what we call a positive, or a converging surface, because it converges the light rays. We have the apex, which is the center of that converging surface, and it also is also the point at which the principal axis runs, or the optical axis runs. We have the center of curvature of the surface, and these dots you see running here are normals. So this spot we have a normal, this spot here we have a normal. Each spot that you can find on this curvature will have a normal. Here now we have the focal point. As the rays come in and they hit the surface, they go towards the normal, as we said before, from a less dense medium to a more dense or denser medium. We have converging towards the normal. So as they all converge, the point to which all these rays meet is the focal point, or the secondary focal point. Secondary because it comes from the primary medium to the secondary medium. So there we have the secondary focal point. Down here we can see the distance from the surface, or the apex of that surface, to the secondary focal point. We call it the secondary focal length. This is for a positive surface. How about a negative surface? So for the negative surface here, we have again the refractive index of the primary medium, refractive index of the secondary medium, and now we have the light rays coming in left to right, and as they hit the surface, the divergent surface, it diffracts away from the optical axis, or from the principal axis. As you can see, they go away. However, they still do go towards the normal, because as I said before, less dense to more dense or denser medium, it will go, always will go towards the normal. Here again, the apex, center of curvature, and the secondary focal point. As we can see, it's on this side now. Why? Because in a divergent surface, the light rays already go away from the principal axis. We have to trace it backwards, and we'll talk about this later, we have to trace it backwards, to which it will form what we call a virtual image. We trace it backwards to find the secondary focal point. Hypothetically, this is where all of these rays will converge or will meet. And here again, from the secondary focal point to the apex, we have the secondary focal length. What about primary focal points? So again, we have a refractive surface. We have light rays rather now going from right to left. We are still going to use the same refractive indexes as before, or indices I should say. And as they go from left to right, it's still going to converge, but this is what we're reversing what we did before. So we go in this direction, right to left, and as they refract, they go away from the normal, because we are going from a denser material to a less dense. So we're going away from the normal, each light ray away from the normal, and the point at which all of them converge, we call it the primary focal point. And the distance from the primary focal point to the apex of the refractive surface is called the primary focal length. So now we could also have it for a diverging surface. Light rays coming from the right towards the left, denser medium to a less dense medium. They're going to hit the surface and they're going to diverge away from their normals, because again the refractive indices are different. They're going from a larger index to a lower index. It's going to go away. However, to find our focal point, although the light rays diverge away, we're going to trace it backwards, reverse the light rays, and the point at which all of them meet is the primary focal point. Primary focal length, again, primary focal point to the apex or to the middle or to the center of the refractive surface here is our primary focal length. So I did mention real and virtual images and so forth, and we would get a great understanding of that through retracing of refractive surfaces. And retracing is what helps us to locate image or to find out its magnification and other components of the image or even the object as well. So let's look at retracing. The first thing let's look at, refractive index again. We have a less dense, more dense over here. We have a converging or convex plane. The first line we're going to look at is the one that runs parallel to the optical axis. So this green line here, as we see, it runs parallel to the optical axis. It refracts at the principal plane and it goes through the secondary focal point of the surface, and we extrapolate that line to run straight down. And then the second line we're going to draw is the line that runs through the primary focal point, and as it runs through the primary focal point, it's going to refract at the principal plane, and then it's going to run parallel now to the optical axis. So it's basically the reverse of the green or the first line that we drew. So it's going to intersect at some point. However, before we decide that that's the image point or that's where the image will form, the third line you draw is a line directly from the object through the center of curvature of the refractive surface. So we draw that line straight through and we see where it intersects, and where that intersects is where the object will be formed. Sorry, rather, is where the image will be formed. And as we can see, H prime is the height of the image. And we have H here, which is the height of the object. We have the focal points, primary, secondary, apex, and also the center of curvature. Something to note, how do we know that the image is real? Real images real images, are formed by converging refractive surfaces. Another thing that we would like to note here as well is that if we calculate the magnification of this system and the magnification is negative, so a negative magnification, that indicates to us that the image will be inverted, or the image is inverted. So when this image is inverted, the magnification should be negative. Once it's a convergent system, your image should be real, or will be real. So let's look at a convergent system now. Sorry, a divergent system now. As we have it here, less dense to a more dense medium. We have the object, and we have our first line. As I said before, our first line runs parallel. It refracts at the principal plane. In this case, it diverges. However, remember that our parallel line, our first parallel line that runs parallel to the optical axis, it always runs through the secondary focal point. So we hypothetically draw back that line, extrapolate it backwards to meet the secondary focal point. What does our second line do? Our second line runs through the focal point, or rather the primary focal point of the surface, of the refractive surface. However, as we can see, as it refracts here, it actually refracts or diverges parallel to the optical axis. So like in the first example, it passes through the primary focal point and then it also runs parallel to the optical axis. But however, we need to, since it's a divergent system, we need to extrapolate these rays backwards to see where they meet. So we have the green and the orange meeting there. Our last ray is the ray that runs through the center of curvature of the refractive surface. As we run that through and we look at where it intersects, all three intersect here. So this is where our image will be formed. And as we can see here, H prime is the height of our image, H height of our object. In this case, once the system is divergent, we call it, in this case, once the system is divergent, we call it a virtual image because it's a divergent system. Also, if our magnification is positive, then we know, this is after calculations, then we know that the image will be erect or upright. So now that we have gone through retracing of the refracting surfaces, we are now going to go into what we call thin lenses, and this will be the last part. Then we'll do some examples just to clarify certain things. So as we can see here, we have 8 different types of thin lenses. We have the equiconvex, the plano-convex, biconvex, converging meniscus, equiconcave, plano-concave, biconcave, and diverging meniscus. For these lenses, as we can see, there are 2 refracting surfaces. Before, we were dealing with one refractive surface or one principal plane, but these will usually have 2 since there are 2 surfaces. However, to find the power of our thin lens, we have P, which is the power, is equal to P1 plus P2, or the power of the first principal surface plus the power of the second principal surface. But remember, P was equal to n prime minus n over r. Spoke about that before. So therefore P2 as well is the reverse of the refractive index, n minus n prime rather over r. And one other thing to note, how do we find, or how will we be able to find the focal lengths of the thin lens? It's simply P is equal to minus N over F. As we can see, this will be for the primary focal point. So how about the secondary focal point? We'll still have, in this case it wouldn't be minus, it will be plus N over F prime. This isn't N prime because in thin lenses we actually aren't going to consider the refractive index of the lens itself, because in thin lenses we are dealing with relationships that we call para-axial relationships or para-axial angles, where the angles are small enough or negligible in these cases. So for example, let me direct you to the image of a thin lens perhaps. In this case we have the object, light being diverged from on the object, light passing through now the thin lens. So we have P1. Now light is passing through P1, the first principal surface, passing through the lens of a different refractive index. It then refracts again at P2. You have an image forming as well. This dashed line is where the image would have formed if there wasn't another refractive surface before it formed this image. So again, this dashed line, it simply indicates where the image would have fell if this second refractive surface was not in the way of it forming the image. However, the angles in this system is so small that we take into consideration what we call para-axial relationships or para-axial angles, meaning the angles are small and we can ignore them for now, and therefore we can ignore the refractive index of the medium, and therefore the lenses in a thin lens, or the refractive surface in a thin lens, it looks more like this. This is indicative that it is a positive surface. We have our primary focal point, our primary focal length, secondary focal point, secondary focal length, and our refractive indices. As you can see, we ignore the index of the of the refractive or the thin lens surface. How about for a negative surface? So we have our negative surface here now. Secondary focal point on this side, secondary focal length, primary focal point, and primary focal length. To help us understand all the relationships that I spoke about just now, we're going to go into a few examples. Hey guys, as you can see, this video is almost 40 minutes long. So what I will do, I will put the examples in another video, so that will be light, refraction, and thin lenses part 2. So you can check that out for the examples. Peace out. Bye.